When an inductor is in series with a resistor, the electrical flow changes due to Lenz's law. When the battery is connected, the current would be the EMF provided by the battery divided by the resistance of the circuit, if there was no inductor. As the inductor is in the circuit, the current in the resistor corresponds to the difference between the two EMFs, the constant battery and the variable inductor. As long as the EMF from the inductor is present, the current in the resistor will always be less than the maximum. As more time passes, the induced EMF by the inductor will tend towards zero, and the current will head towards its maximum. The EMF provided in an LR circuit is given by the EMF provided by the battery, the current and the resistance flowing through the resistor, plus the EMF provided by the inductor. Solving this differential equation gives an equation for the current being equal to the EMF provided by the battery divided by the resistance outside of 1 minus e to the minus the resistance times time over the inductance. E to the negative RT on L can sometimes be written as e to the minus t on tau, as this tau is equal to L on R for a LR circuit. So how does the current and EMF change with time? So graphing the equation for a charging LR circuit, we get a graph that looks like this. In this equation, we have that VB here is the voltage of the battery. We've got tau here as our time constant. As the circuit has got all the charge going through, now we must look at what happens when the power supply is removed. This graph shows the decay of the inductor. The equation follows that the current is equal to the EMF provided by the battery divided by the resistance, e to the negative t, the resistance, divided by the inductance. The EMF provided by the battery divided by the resistance is I0, the initial current of the circuit. So this can also be written as the current is equal to I0 e to the minus time times resistance divided by inductance.